In this video, we're going to talk about something completely different from what we have been doing. There's going to be no integration in this video at all. Instead, we're going to talk about something called a sequence. So first, let's give our definition of what a sequence is. A sequence can be thought of as a list of numbers and this list of numbers is going to have a definite order. So my sequence is A1, A2, A3, and so on. It has a very specific order. We usually put curly braces around our sequence, so it looks like that. And this is also denoted by just curly braces with an AN in it, or with AN and then we specify n equals 1 to infinity. All of these mean the same thing. It's just A1, A2, A3, and so on forever. So we have infinitely many numbers in this list and they have a specified order. Now, sometimes our sequences aren't listed like this. Sometimes they are given to us by a formula. So here's examples of some other ways of writing sequences. So this is just an example of different ways to write a sequence. So my first example, I'm going to have n over n plus 1 when n is 1 to infinity. So that's one way of writing a particular sequence. We could also just specify that my nth term is equal to n over n plus 1. Or I could write the same sequence by just plugging in various values for n and seeing what I get. So when I plug 1 into this sequence formula, I get 1 over 1 plus 1, which is 2. When I plug in 2, I get 2 over 2 plus 1, which is 3. Then I keep plugging in, get 3/4, 4/5, and so on. All of these are the same exact sequence that we have, it's just listed in different ways. I personally happen to like this first way, or the way where you define the nth term, but sometimes people really like to see it listed out like this. But they all mean the exact same thing. Another example of a sequence written 3 ways. -1 to the nth power times n plus 1 over 3 to the nth power. And I'm going to not write the n as 1 to infinity this time, though you could. That's a valid way to write it as well. I could also write that the nth term is -1 to the n times n plus 1 over 3 to the n. Or we could list out a bunch of terms like we did with the last one. So if I plug in a 1 for my n, I'm going to get -2 over 3. And when I plug in a 2 for my n, it's going to be positive 3 over 9, which we could simplify. I'm just not going to right now. My next term would be -4 over 27. Then we get 5 over 81. And so on. All of these are just different ways of writing the same sequence. All right, so sometimes you're given things like this, and other times you are given a list and you have to come up with the formula yourself. So let's find a formula for the general term an of the sequence given by 3/5, -4/25, +5/125, -6/625, +7/3125, and it keeps going. So there's our sequence, and in order to write a general term for this sequence, we're going to have to recognize a pattern of what's going on. So let's talk about the pattern. What things do we notice when we look at these terms? Well, the first thing I notice is that I'm alternating in sign. It's going positive, negative, positive, negative, positive. So it alternates in sign. And that means I'm going to need either a -1 to an n+1 or a -1 to the n-1, because when I plug in a 1 for my first term, I should have something positive. So I need an even power on my -1. I also notice that my denominator is a power of 5. The first term has 5 to the first, second term has 5 squared, then we have 5 to the third, 5 to the fourth, 5 to the fifth. So I know I have a 5 to the n in the denominator. And then what about the numerator? If we ignore the plus or minus, because we already took care of that, the numerator just increases by 1 each time. But my first term starts at 3. 3 is equal to 1 plus 2. 4 is equal to 2 plus 2. 5 is 3 plus 2. So I know I'm going to have an n plus 2 in the numerator. Because no matter what n I plug in, I'll have 2 more than that in my numerator. So that means I can write the general term for the sequence just by putting all of this together. an is equal to a -1 to the n+1 times n+2 all over 5 to the n. And you could also write that -1 to the n-1 power. That would also be correct. It would work exactly the same. There's more than one way to write your sequences. If you're ever doubting the pattern you came up with, just plug in values for n to see if it matches what you had to begin with. Now, just because I'm emphasizing the pattern on this sequence and knowing that we're going to have to find patterns sometimes, that doesn't mean that there's always a pattern to every single sequence. You can have sequences that don't have a pattern at all. Remember, a sequence is just a list of numbers that have an order. So for example, of those, not all sequences have a simple defining equation. For example, I could have a sequence that I'm going to call Pn, where Pn is the population of the world on January 1st in year n. So there's going to be a specific order to this list of numbers because I'm increasing in time. Each year I would have a new number to have in my population sequence. But you can't expect there to be a nice pattern to it. Population is going to vary depending on the births and deaths in that particular year. And there's no way to come up with a nice formula that's going to represent the sequence for every single year. Another example of a sequence that doesn't have a nice, simple defining equation is we could let an be the digit in the nth decimal place of the number e. We know e is a nice irrational number. My an would start with 7, 1, 8, 2, 8, 1, 8, 2, 8, 4, 5, 9, 0, 4, 5, and 2. And that's as far as I have memorized. You don't need all of that memorized. This sequence would go on forever. And of course, yes, there's a 2 at the beginning of E, but I'm talking about in the decimal places after the decimal point. There's no specific formula that will generate the next digit of E for you. It would just go on forever with a specific order, but no equation defining it. So we have sequences with a nice equation defining it. We have sequences that don't have a nice equation. We can also have sequences that are defined recursively, and that just means the terms of the sequence are defined in terms of previous terms of the sequence. So what do I mean by that? Well, one very famous sequence is called the Fibonacci sequence, named after the mathematician Fibonacci. I'm going to call it Fn. It is defined recursively as F1 equals 1, F2 equals 1, and Fn is equal to Fn minus 1 plus Fn minus 2 for n greater than 2. So what is this saying? Well, it's giving me my first two terms, 1 and 1. And then it tells me my third term will be the sum of the second and the first. So I just have to add the two previous terms to get the next term in the Fibonacci sequence. I start with 1 and 1, and now I'm going to add the two previous terms. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 22, and it keeps going forever. You get the next term by adding the two previous terms. Except I can't add. This is not a 22, it is a 21. 13 plus 8 is 21, not 22. But you just get the next term by adding the two previous terms. So my next one would be 34. Now, why are we talking about all these sequences, and when is the calculus going to come in? Well, we're going to be talking about limits of the sequences. So hopefully you remember more limits from Calc 1. And we talked a little bit about limits in our last video when we were doing improper integration. So hopefully you're a little familiar with them. So a sequence AN has the limit L, which we can write as the limit as n approaches infinity of AN equals L. If we can make the terms AN as close to L as we like, by taking sufficiently large n. So what we're saying here is the values in our sequence are going to get closer and closer and closer to a particular number. And as long as we can make those terms get as close as we want to that particular number, when I go far enough out of my sequence, we say that the limit is equal to that number L. If the limit exists as a finite number, we say that the sequence converges. And otherwise, it diverges. Now, those are terms that we used just in our last video on improper integrals. Remember, our improper integrals, if the limit was finite and existed as a finite number, we said the integral converged. And if we got something infinite or the limit did not exist, it diverged. Same with sequences. It's the same terminology with a slightly different concept. Let's have a theorem for us. If the limit as x approaches infinity of some function f of x equals L, and the value of our function when I plug in an integer n is equal to an, the nth term of a sequence, then the limit as n approaches infinity of an is also L. So what this is saying is that if I'm trying to find the limit of a sequence, I can look at the limit of an associated function instead, and then calculate all my limits the way we used to do in Calc 1. Why is this important? Well, because remember there were some limits where it was very handy to use L'Hopital's rule. But L'Hopital's rule has a very strict set of conditions. We have to have functions which are differentiable in the numerator and denominator and have it 0 over 0, infinity over infinity. So if I just had terms of my sequence, I cannot use L'Hopital's rule directly on a limit of sequence terms. But I can rewrite with an associated continuous function f of x, and it would be a differentiable function, and then I could do L'Hopital's rule on the associated function and still get the result for my limit. And I know that sounds very, very nitpicky, but all I'm saying is if you're trying to find a limit of a sequence and you think you're going to need L'Hopital's rule, you need to rewrite it with x's instead of n's so that it fits the conditions of L'Hopital's rule, and taking a derivative will make sense. All right. Let's do some limit laws for sequences. Remember, we had a bunch of limit laws for when we were taking limits of functions back in Calc 1. And a lot of those limit laws extend to sequences as well. If an and bn are convergent sequences, and c is a constant, then we have a bunch of limit laws. Our first one is the limit as n approaches infinity of an plus or minus bn is equal to the limit of an plus or minus the limit of bn. So the limit of the sum is equal to the sum of the limits, like you would want it to be. Notice that we do have to have convergent sequences for this to be true. My next limit law, the limit as n approaches infinity of a constant times my an is equal to that constant times our limit of an. That should look very familiar from Calc 1 as well. If you just multiply by a number, that number can be pulled outside of the limit. the limit as n approaches infinity of an times bn is equal to the limit as n approaches infinity of an times the limit as n approaches infinity of bn. So the limit of the product is the product of the limits. Again, if your sequences are convergent sequences. Similarly, the limit of your quotient is equal to the quotient of the limits if we end up not dividing by 0. So you can't have the limit of bn equals 0, but as long as it's not 0, then the limit of the quotient is the quotient of the limits, provided you have convergent sequences. And one more limit law is that the limit as n goes to infinity of the terms of your sequence to a power is equal to the limit as n goes to infinity of your sequence to a power. If the power is bigger than 0 and your ANs are also bigger than 0. So that says you can take the limit of the sequence first and then raise it to a power. Now, when you first learned limits in Calc 1, you also learned something called the squeeze theorem. And we have a similar squeeze theorem for sequences as well. So our squeeze theorem for sequences says that if an is less than or equal to bn, which is less than or equal to cn, for all n greater than or equal to some particular value of n, and if the limit as n approaches infinity of an equals the limit as n approaches infinity of cn and is some number L, then the limit of the bn is also L. So this is saying if I have 3 sequences and they're organized in such a way that one is always the biggest and one is always the smallest and there's one in the middle, then if the two sequences on the outside, the smallest one and the biggest one, converge to the same value L, then the guy in the middle has to converge there as well. He gets squished in between the bigger and the smaller ones, and they all converge to the same value. One more theorem about limits of sequences. If the limit as n goes to infinity of the absolute value of the terms of your sequence equals 0, then the limit as n goes to infinity of your sequence without absolute values is also 0. So all of these limit laws and these theorems can be used to help us find the limit of a sequence to see if the sequence converges or diverges. So now let's do some examples determining whether a sequence converges or diverges. Let's find the limit as n goes to infinity of the natural log of n over n. Let's take a look at what we have here. I can think about just plugging in and going to infinity, but then I would have infinity over infinity. And that sounds like a situation where I'd want to use L'Hopital's rule. The problem though is L'Hopital's rule requires that I have differentiable functions. And right now I don't have differentiable functions. I have just discrete points because my n's are only integers. It's not all real numbers. So that means let's look at the related function and do a limit of that. We're going to apply L'Hopital to the related function f of x equals natural log of x over x. Because I had that one theorem that said if the limit of a function is a particular value and that function evaluated at integers equals the terms of my sequence, then the limit of the sequence equals the limit of the function. So I'm going to find the limit as x goes to infinity of my function, natural log of x over x. Now, using my L'Hopital's rule, I know I can take the derivative of the top and the derivative of the bottom. The derivative of the top is 1 over x, derivative of the bottom is 1. So now I just have a limit as x goes to infinity of 1 over x. And so now as my x grows, I get a smaller and smaller value. So this limit goes to 0. So this limit goes to 0. And so my limit as n goes to infinity of natural log of n over n is also 0 by that theorem that said we could look at the associated function. All right, well that wasn't too bad. Let's figure out if a different sequence converges or diverges. This first one that we had converged to 0. So is the sequence an equals -1 to the nth power convergent or divergent? Well, if I just list out terms of the sequence, when I plug in 1, I get -1. When I plug in 2, I get +1. Plug in 3 and get -1. Plug in 4, get +1. And it keeps going like that forever. Does it look like this sequence is approaching any particular value? No, it's just alternating back and forth between -1 and 1 and not getting close to any particular value. So this means that this sequence is divergent because the limit as n goes to infinity of this sequence does not exist. I just keep alternating back and forth between -1 and 1. Let's do another example. Evaluate the limit as n goes to infinity, -1 to the n over n, if it exists. Well, I had one particular theorem that involved absolute values. I had a theorem that said that if the limit of the absolute value of a sequence goes to 0, then the limit of the sequence without absolute values also goes to 0. Let's try that theorem out on this problem. We know that the limit as n goes to infinity of absolute value of the terms of my sequence is equal to the limit as n goes to infinity of 1 over n. And this goes to 0. So by our theorem, the limit as n goes to infinity of -1 to the n over n has to also be 0. Notice though that that theorem did not say anything about if the limit of the absolute value is anything other than 0. It only works if the limit of the absolute value equals 0. it doesn't, then you got to try something else to figure out if your sequence converges to 0 or converges to whatever. All right, let's have another theorem. This is a theorem about continuity and convergence. Which says if the limit as n goes to infinity of an equals L and the function f is continuous at L, then the limit as n goes to infinity of the function with terms of our sequence plugged into it is equal to f of L. So you can think about this as passing the limit through the function, taking the limit of the sequence, and then plugging that in as an input to our function. So let's use that theorem on our next example. Let's find the limit as n goes to infinity of sine of pi over n. Well, let's first ignore the sign for a second. First, just look at pi over n. The limit as n goes to infinity of pi over n, that goes to 0, because I have pi divided by bigger and bigger numbers. And we know that sine of x is continuous at 0. So using that theorem we just had written down, my limit as n goes to infinity of sine of pi over n is equal to sine of my limit as n goes to infinity of pi over n. Well, that's sine of 0, which is 0. And so I have that my limit is equal to 0. Since my function was continuous, I was able to pass that limit through the function, take the limit of the sequence first, and plug the result into my function. Let's try a harder sequence. Does the sequence an equals n factorial over n to the n converge? Now, before I try to discuss the convergence of this, let's quickly remember what a factorial is, because I know some of you might not know this. That little exclamation point symbol is called factorial. And we should know that n factorial is equal to n times n minus 1 times n minus 2. Keep multiplying until you reach 1. And 0 factorial is defined to be 1 just by definition. So what this is saying is you take the number n and you multiply it by 1 smaller all the way down until 1. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. So that's all that a factorial means. So we want to figure out if this n factorial over n to the n converges or diverges. And if you think about it, well, as n gets bigger and bigger, this n factorial is going to get really big, and so is n to the n. We have like an infinity over infinity. So your gut instinct might be to do L'Hopital's rule, but unfortunately that's not going to work too well because this factorial is only defined for integers, and we would need a continuous function like x factorial, but it doesn't make sense with our definition to do like 5.5 factorial. That doesn't make sense. We can only have integers in it. So I cannot use L'Hopital because x factorial would not be defined for non-integer values. So we have to just play with this differently and see what happens. So let's take a look at our an written out. I know an is equal to n times n minus 1 times n minus 2 times 3 times 2 times 1. And n to the nth power is n times n times n all the way through n. This happens n times. So I have n terms on the top being multiplied together and n terms on the bottom being multiplied together. Let's rewrite this in a very interesting way. I'm going to take the very last guys and pull them out front, 1 over n. And I'm going to multiply that by everything that's left behind. I have n, n minus 1, n minus 2, all the way through 3 and 2. And I have n times n times n, all the way through n. And I have an equal number of terms on the top and on the bottom. Now, if you look at the parentheses here, n over n would be 1. But everything else, the piece on the numerator is smaller than the piece in the denominator. So I know everything in this set of parentheses is at most 1. And in fact, it's likely smaller than 1. It all depends on what your n is. But you can see that I have a smaller numerator than I have a denominator. So everything in the parentheses is at most 1. And that tells me that this an is going to be smushed in between 1 over n times 1 and 0. Because I always have a positive number for my an, and it's less than or equal to 1 over n because an equals 1 over n times something that's at most 1. Now I can use my squeeze theorem. My squeeze theorem tells me that if the limit of the smaller guy, which is the limit of 0, and the limit of the biggest guy, which is also 0, if those two limits are the same, which they are in this case, then the guy in the middle also has to have the same limit. So by the squeeze theorem, we have that the limit as n goes to infinity of n factorial over n to the nth power is also equal to 0. And that's why it's good to have theorems like the squeeze theorem, because then we can sometimes find the limit of more complicated things without having to do too much work. Taking the limit of 1 over n and taking the limit of 0 are both pretty darn easy to do, and we just get the limit of the middle guy just by default using this theorem. All right, so that is a lot about sequences. And in my next video, I will talk about a specific type of sequence called a monotone sequence. Monotone sequences have certain special properties that allow us to do more things with them. So stay tuned for that in the next video. If you have any questions, feel free to drop them below. If you're a current student, you can also ask in office hours or through email, and I'll see you guys next time.